Now let's get a little bit more into the use of the energy expressions for rotational transition. Notice that we've switched from using L to J here to keep from double using the letter L. So L is going to refer to vibrational transitions, whereas J will refer to rotational transitions. And we've defined this term called beta. That's going to be our rotational constant. Remember, mu is reduced mass here. R0 is the distance between those two reduced masses on the rigid rotor. So mu r squared is the moment of inertia. We have our quantum number, and then h bar squared over 2. So we could separate that into h squared over 4 pi squared, and so we have h squared over 8 pi squared total here, and then that moment of inertia term. And we're going to define this constant beta as h over 8 pi squared times speed of light times moment of inertia. So these are all either constants or constants associated with a molecule. We include the speed of light there just to change the units from hertz to wave numbers on beta. And since the selection rules state that delta J has to be plus or minus 1, it can be shown, and we'll show this on the next slide all in one shot real quickly for the derivation, that delta E for rotational transitions is 2 times h times speed of light times b times j plus 1 for upward rotational transitions, and for downward rotational transitions it's minus 2 h c b j. And like I said, we'll show that on the next slide. But one thing to notice there is that delta E plus and delta E minus are not equal for any particular energy level, because the energy levels are not evenly spaced. Since rotational energy does not depend on m sub L, each level is going to be 2j plus 1 degenerate. That means there's going to be 2j plus 1, where each energy level is denoted with a j, equal energy on each level. Here's the derivation as promised. If we want to know what change in energy is going to be for a energy level going from some energy level j up one level, remember that the initial energy is going to be h bar squared over 2 moment of inertia times j plus 1. So moving to the next energy level up would add 1 to each of these expressions. We FOIL, we distribute, and then we can factor out this constant fraction to the front. We take the difference between these two expressions and we get j plus 1. And then we can substitute beta in, and we get exactly what we promised. Now when j is going down, instead of adding 1 to each of these for our final energy, we subtract 1. So this goes from j to j minus 1. This goes from j plus 1 to j. Again, we distribute, we take the difference, and we get something different, negative 2hcbj instead of bj plus 1. Now frequency measurements can be made with a lot of precision, so bond lengths can be determined with very, very high precision. So if I give you the rotational constant out to 7 significant figures for HCl, and give you the masses out to even more significant figures for those two atoms, you should, based on everything we've been able to talk about, determine the bond length of HCl to extremely high precision. So try that out. Pause the video, write this question down, and try that out on your own as you get chance between now and the next time we meet. Actually, it may take us till the following time to get to this particular problem. In the meantime, if we're looking at a rotational spectrum, how many peaks should we see? Delta J has to be plus or minus 1 But the energy of rotation is far less than kT. So this isn't like vibrational spectroscopy when almost all the molecules are at the energy level of zero. Many rotational levels are going to be populated. And the question is, how far apart will each of those peaks be in our spectrum? Well, going from 0 to 1 is going to have a delta E of 2CB. So it'll absorb at the 2CB level, where B is the rotational constant and C is the speed of light. It'll also absorb at the 4CB level, which is 2 larger than the 2CB. And the same thing for at the 6CB level, which is 2 larger. So we're going to see a bunch of different lines in our spectra that are equidistant from one another as a result. Let's see what I mean by the difference in energy values for these transitions. A rotational energy is going to be equal to this expression as we talked about earlier. Vibrational equal to this as we talked about earlier. So we can reduce that fraction a bit and get that the fraction between these two, the fraction of energy associated with rotation compared to vibration, is h bar over r squared times the square root of spring constant times reduced mass. We put all the appropriate numbers in for hydrogen molecule and we get 0.028. So there's only 2.8% the amount of energy associated with the smallest rotational transition compared to vibrational. For I2, we put in the numbers associated with I2 and we get an even smaller number, less than a percent. Far less than a percent, in fact. So if we think about that in terms of a Boltzmann distribution, where we look at the difference in energy between two rotational states, and we characterize that here, the degeneracy term dominates for small j and for large t for high temperatures, especially for molecules with a large moment of inertia. And this causes molecules with large moments of inertia, heavy or long radius molecules, to have many occupied rotational levels at room temperature, such that delta E for rotation will become larger and on the order of delta E for vibration. Let's take a look at the rotational spectrum for carbon monoxide. Here's exactly what we're talking about. This we call the P branch. These are all -1 transitions, whereas the R branch is all +1 transitions. And so this is going to show up in an IR spectrum as being a very broad, unresolved pair of peaks, unless we're using an extremely high precision instrument. Your textbook does a pretty good job in section 8.7 of going over the mathematical basis for a Fourier transform. It's a little beyond the scope of a PChem course. I'll leave that for you to deal with in a different course, but if you're interested, or if it maybe does gives a different perspective on the explanation of FT than you've gotten in other courses, then it might be useful for you to take a look at.